welcome everybody to this new webinar. We're following up on our series of webinars here at NanoE. Today we're going to talk in general about metal additive manufacturing technologies. There's a lot of different technologies available on the market, and sometimes it's a bit difficult to understand who's who and what is the best technology for your application. And that's what we're going to try and tackle today. Of course, during the presentation and at the end of it, you are most welcome to ask questions, ideally in the Q&A section. You can also raise your hand. There's a small button for that at the end of the presentation, in which case I can invite you to turn on your microphone and camera and ask your questions directly. For those on YouTube, there's also a chat there, so you could also drop any questions you have, and we'll try to answer them at the end of the webinar. I'm going to share a short presentation. Here we are. So let's start. Thank you again for joining this webinar. Today we're going to do a brief overview of, let's say, the main technologies in metal additive manufacturing, to compare them and to see which ones are adapted for which application. Of course, we're not experts in all of these technologies, so I might make a few shortcuts and not be completely exact. If it's the case, I ask you to forgive me. First, a short introduction on NanoE and what we do in additive manufacturing. The company itself first, NanoE. NanoE, we are raw material provider, so that means we produce ceramic and metal raw materials. Not only for additive manufacturing. The company has been active for 13 years, and for almost 10 years, we've been producing materials only for what we call traditional processes, mainly ceramics. So the actual, let's say, historical activity of NanoE is producing ceramic powders, ceramic feedstocks, adapted for industrial processes. We have a strong focus on innovation, which is what led us to additive manufacturing, and I'll go back to that later on. Our materials are, well, raw materials, so they're transformed by our customers to produce ceramic and metal parts with, let's say, three main processes for the traditional way, and of course, there's a fourth one, which is additive manufacturing. The main process used to produce ceramic materials, metal is a bit larger, but for ceramic, the main industrial processes are pressing, casting, and injection molding. And of course, we've added 3D printing to it. I'll go back later on one, which is quite important for us, which is injection molding. You'll see that this is actually the father of our technology for 3D printing ceramic and metals. All of these processes are indirect process, what we call powder metallurgy. That means we just shape a body of powder, usually with binders, but then there's always a post-process, which is sintering, and this is very similar to what we're doing in 3D printing. These materials go in a wide range of applications. They go in aerospace, medical, semiconductors, luxury goods, wear parts, any kind of industries where we need high performance materials. That's really the focus of NanoE, producing high performance materials for the demanding industries. Again, you'll see that with additive manufacturing, this range of application is getting a bit wider. You'll see about that later on. That's it for the general presentation of the company. I just really wanted to focus on one thing. If you need to have one takeaway from this, it's that the core business of Nanui is producing raw materials, producing the materials that goes into an injection printer or an injection machine or a 3D printer. That's just the same for us. And you'll see that we also offer other things, but the core of the technology and the core of what we do is producing raw materials. Note what we do in additive manufacturing. 3D printing is a new diversification we started 3 years ago, but which really comes from our background in materials. We've decided to offer materials compatible with 3D printing, and we launched a technology which is based on filament deposition, FDM, FFF. There's a few different wording for it. Extrusion-based process, let's say. So we've been using what Nanui does best, which is preparing raw materials. And in this case, we've started from what we call ceramic injection molding and metal injection molding feedstocks. I'll go back to that later on, so I'm not going to go too much in details. And these feedstocks, which are a mix of plastic binder and powder, we extrude them into a filament. And that's really the two key points. The compounding and extrusion is what will allow us to make a material compatible for 3D printing. We offer these materials for ceramic and metals. In ceramics, the two main ceramics being alumina and zirconia. And for metals, we have two different kinds of steels. Again, I already said it, but I'm really going to insist on it. The core of our business is raw materials. So the core of our offer is the materials, the filaments, ceramic and metal. We still do offer machines which are compatible with these filaments, because we see that a lot of customers ask us not for a material, but for a solution. They want the material and the compatible machine. So we decided to make that offer, knowing that we're not a machine manufacturer. So we buy machines adapted to our technology, and we just bundle them together and resell. Some of you will recognize the printer, which is a well-known brand. The furnace is a bit more exotic for most people from additive manufacturing, and this is a furnace which is compatible with both metal and ceramics. That was something really important for us. Just to dive a little bit into how to use those materials, and then we'll really get to today's topic. How do we use those materials? Well, it's quite simple. It's a 3-step process. Well, 4 if you add file preparation, of course, or you do the file preparation, which is what we call slicing. And then it's printing, debinding, and sintering. In the case of ceramics, debinding is done chemically. That means we put the part in a solvent that removes at least a part of the binder, if not all of it. Which really makes it a 3-step process. You'll see that for metal, it's a little bit different because we've removed that chemical step. So there's only, physically, there's only 2 steps. Actually, there's 3 things happening. We print, and then we put the part in the furnace. And in the furnace, you actually debind and sinter at the same place. So there's still printing, debinding, and sintering, but printing and debinding and sintering is done in the same machine. It's done thermally by heating up. There's a big difference with ceramic, however, which is that when you sinter metal, you need a protective gas. So here we're using argon for the H13 tool steel. And again, a big difference and a bit still a pain point for our customers is the type of gas you need to use. And for H13, it's quite simple. You can use argon. That's quite convenient. For stainless steel, for the moment, we still need to sinter under hydrogen, which makes it a much more expensive technology, because furnaces compatible with a pure hydrogen atmospheres are much more expensive than furnaces for argon. So that's the general overview of the process for the different kind of filaments. I'll keep, I can see there's a few people starting to ask questions. I think I'll keep the questions for the end of the presentation, but really feel free to write them down and to keep them somewhere. So that's the general overview of what we do at NanoE. We provide filaments. We also provide the compatible machines. And these filaments are used in a process where you print, debind, and sinter, which makes it really the most simple and the most affordable way to print ceramics and metal. So let's dive a bit into the different metal additive manufacturing technologies. First thing is I want to make a small disclaimer. Of course, NanoE is not an expert in all of the technologies I'm going to talk about. We know very well about, let's say, sinter-based technologies, a little bit less about the other ones. So we may make some small approximation, and we may forget some stuff. I ask you your forgiveness, is that the case? And you can certainly correct me at the end in the Q&A section if you have any remark on this. Still, we felt it's important to know the available technologies on the market, the pros and cons, so that you can choose the right technology for your application. That's really our message. Each technology has its niche, its dedicated applications, and we really do not feel at NanoE that we are competing with SLA for ceramics or binder jetting or laser melting for metal. This is really not the case. Each technology is used for different applications. And if you understand that, you can, depending on your application, choose what is the right technology. So for a brief overview, of course, this is schematic. You have a lot of other technologies, but we decided to talk mainly about 5 technologies today. I'll name a few other ones at the end, but let's say the biggest one on the market at the moment. You have what we call direct technologies, powder bed fusion, direct energy deposition, cold spray. And you have what we call usually MIM based technologies. And I'll go back a bit on that. You could also say sintering-based technologies, indirect technologies where you print what we call the green part and then you sinter it to get a dense ceramic or a dense metal. So let's dive in. First technology, of course, probably the most well-known of the metal technology is powder bed fusion. It's the legacy technology, the one that's been active in the market for the longest time, and probably the one that has the most well-known use cases. Now, the first thing is there's a small question here on how we should name it. There's a lot of different way of calling it. Some of them are exactly the same, sometimes it's not the same. We talk about powder bed fusion, selective laser melting, direct laser, metal laser sintering. A lot of these technology, it actually means the same. There's one big difference between laser-based technologies and electron beam melting, which is really basically the same technology, except that the power source is not a laser, it's an electron beam. But apart from that, it is really the same technology, so we haven't made any difference. We feel that for our purpose today, we can say it's in the same family. But all of these are basically the same kind of technology. And how does it work? Quite simply, you have a laser or a power source, an electron beam, it could be, which is directed on a powder bed. So you put a layer of powder, and with a laser or another power source, you're going to melt or sinter selectively the powder where you actually want your part to be solidified. You do your layer, and then the build platform will go down. The leveling roller will add another layer of powder, and you repeat. This is a very well-known technology. It's really the leading technology on the market. In terms of pros and cons, we would say it has a good resolution. It's probably, and that's the most important thing, the technology which will give you the highest strengths in a printed part. It's a very robust process. It's been on the market for a long time. So everybody, well, not everybody, but a lot of people know how to use it. It's been used for critical parts. So really, this is something reliable, something everybody knows about. There's a lot of material available because, again, the technology has been on the market for a long time. There's a few materials that are difficult, though. Copper has been a challenge for a long time, even though it's starting to be coming in the market, but it has been a challenge with laser-based process for a very long time. In the cons, well, the first thing, it's an expensive technology. You have a high expenditure, capital expenditure for a printer which does not have a huge productivity. So that means basically the capital expenditure per part is going to be quite elevated. So you need to focus on high-end parts. You have to. If not, you won't be able to have a business case here. There's a problem with supports. You need a lot of supports to print a metal part with this technology, and these supports are really attached to the part. So you need to remove them afterwards by cutting them. It's a quite tedious process. And on the cons also, well, you are handling metal powders, which may seem obvious, but not all technologies need to handle metal powders. And metal powders are a serious hazard, both in terms of health, also in terms of danger of explosion. Metal powders are usually inflammable and explosive, which means if you want to do this in a safe way, you actually need quite a complex environment. You, of course, need protective gas, but you also need probably your workers to be in specific outfits with protective gears. Well, this makes it really, let's say, a heavy investment, both in capital and in environment. There's also, but a lot of process have that, a lot of thermal stress on the part, which can lead to deformations, which can lead to a few problems. That's one of the disadvantages of this technology. Typical applications, I told you, well, the bottom line of all of this is it makes great mechanical properties, but it makes expensive parts. So you need to find applications where you can really add some value. And that means it's a lot of critical parts for quite demanding industry, aerospace, some automotives, but let's say high-end automotives, medical, that's the kind of industry where you will find a lot of powder bed fusion. Here we have a few examples which are really well known. The credits are for GE and Bugatti. GE is probably one of the first companies who made an industrial scale production of parts using selective laser melting. I'm saying it's one of the only one of the first one, probably not the first one. There's been some other examples, and I'm thinking of Michelin in France, but still it's an interesting part. It's a fuel injector for a motor, an airplane motor. And the interest here of additive manufacturing was the possibility to print an extremely complex part, and in the end, to integrate in one part something that was prior done with assembling a lot of different subcomponents. And by printing just one part instead of manufacturing tens of components and assembling them together, you can actually end up with a better product, but also a product that for the overall cost is actually cheaper than would be the assembled system. In the case of Bugatti, it's really, well, both a technical demonstration because the part is very impressive, and also interesting in terms of mass optimization, which is one of the big interests of metal additive manufacturing. which is to put the material where you need it and not where you don't need it. And that allows much lighter yet very efficient parts. Powder bed fusion is 50% of the market. It's the big thing at the moment, and we can name a few. I mean, it's not exhaustive, of course. I'm sorry for those I forgot. I try to be as much exhaustive as possible. The leaders will be EOS, of course, and GE additive. That's really the two leaders. You have a few big names, Trump, SLM, to this system, of course. In France, there's ADAP, which is also a great solution, and you have quite a lot of new companies that are trying to tackle the entry level of selective laser melting. I'm thinking about Exact Metal, One Click Metal, and there's probably some other ones. I must say, again, this is not exhaustive, and I ask you to forgive us if we missed your company. So a lot of players here with very different approach. You have some very industrial printers, and I'm thinking about AOS again, SLM, GE with multi-laser printers, very big print size, and so on. And you also have complete opposite One-Click Metal and Exact Metal who are trying to make the technology as affordable as possible. And the rough idea is it will range from 100,000 euro for the smallest equipment up to several millions for very big equipment. Second technology is direct energy deposition. Well, there's a lot of things in that process, a lot of potential different feedstocks and source of energy, but I'm going to simplify a bit. Usually, what does that mean? Direct energy deposition. You have a print head, which is usually, not always, but usually on a robotic arm. You have a supply of metal, which can be wire, powder, and sometimes different things, but mainly wire and powder. And you have a power source. Here we mentioned laser, but it can also be other power source, electric arcs, plasma, whatever energy source that will allow you to melt the metal that you're feeding. And you have a platform. Actually, the platform sometimes moves and sometimes don't, because you have a robotic arm, so the robot can do everything it needs be. Sometimes it will just turn. Well, a lot of different configurations here. But basically, the idea is we bring some metal supply and we melt it and deposit it on the part. Now, this is really a very different technology with some big pros and some big cons. You'll see. In the big pros, it's a very high build rate. Again, depending on the kind of machines, but it can go to very high build rate. It makes relatively dense parts. It's one of the only one where you can print a part, but you could also just repair a part. That means bring some material on a part that is already existing, which is really of interest for a lot of industries. It allows to make very large parts. It's probably one of the best technology for that. And it also has a multi-material capability, because you could, at any point in the printing, you could change the feed with another material and start printing with a second material, or even make gradients of material. On the cons, again, it's a very high capital expenditure. Again, this is schematic because you have a lot of different machines on the market, but it's usually quite low resolutions, quite big installation, quite complex implementation, especially if you're using metal powders again. You also have a lot of thermal stress on the part, and in general, the printable geometries are a lot more limited than with selective laser melting. A nice example of part that was printed recently by Naval Group. This is a propeller for a ship. You may ask why the hell should we print that instead of manufacturing it in another way? Well, there's a few good reasons. One of them being it allows to make the part on demand. The other one being the part is actually hollowed out. It's not fully dense, which makes it a lot lighter and could have interest in terms of furtivity of the ship. So there's really a business case for that. And obviously, there's not a lot of technology which could print a part that big. You can see the operator on the side, so you can imagine the size of the print is really massive. Direct energy deposition is something in the range of 15% of the market. Of course, the figures are very rough. They come from one market study. It's always difficult to answer. So here we named a few names. You have a lot of players here, especially since there's a few different way to use the technology. Some people will have a powder feedstock, some people will have a wire or even a strip or whatever. There's a lot of different feedstocks, a lot of different energy source, so it's difficult to be exhaustive here. So I named a few names. There's some French here, BIM, which is part of additive, Prodways. You have companies like Jeffertech and WAM, which are quite well known in that market. You also have, just like with selective laser melting, some companies trying to go to the, let's say, the entry-level systems for smaller parts, but still something more affordable to start the technology. And here, for me, the big name is Meltio for that entry-level segment. That's it for direct energy deposition. And the last, let's say, direct process, which is quite significant at the moment, is cold spray, which is very different here because you don't actually melt the material. How does it work? So again, you usually have a robotic arm. It can be different according to the kind of printers you're using, but one of the most well-known brands will use a robotic arm and what we call a cold spray nozzle, which basically will propel the powder on the part at supersonic speed, so extremely fast, but with almost no heat, which is why we call it cold spray. So it's not completely cold, but it's way below the melting temperature of the metal. And the way you densify the metal is not with thermal energy, it's with kinetic energy. You project the powder so fast that it will actually densify when it comes on the build platform, on the build part. So it's a very interesting and original technology with, again, high build rates. It does make dense metals, and it's a cold process. So that allows you to do very different things, and it can be interesting for some applications. On the cons, it's again quite high capital expenditure. It has, well, for someone who's used to selective laser melting or to FDM or binder jetting, it has a very low build resolution. So it's really not for the same kind of applications. It is still quite complex environment. You are projecting metal powders at very high speed, which means you have powder everywhere in the machine, which makes it a bit complex in terms of implementation. And the printable geometries are quite limited. You can't do everything. You can't do any close porosity, for instance, any porosity at all, actually. There's a few limits here. Quite often, actually, with cold spray and direct energy deposition, in a lot of cases, the part will be post-machined after printing. That's really very often the case. Here, just two names. There's some other ones, of course, but I would say that's the biggest one, Speed 3D and Titomic. Now we're going to go to MIM-based technology, sinter-based technology. I'm going to start by a short introduction on what does MIM means. And even prior to that, say that, well, this is an area where we see a lot a lot of new technologies emerging, so I'm not going to be exhaustive. It's not possible. They all gravitate around the same kind of concept at the beginning. It's always a bit the same thing. So I don't think it's a major thing if it's quite complex to make a full map, let's say. So what is MIM first? Here we go. So MIM is an industrial process to manufacture metal parts by sintering. How does it work? It's a quite several-step process where you mix metal powders with binders. You make them into granulate, and these granulates will be injected in plastic injection molding machines. Well, adapted plastic injection molding machines, but very close to plastic injection molding. So what's a plastic molding machine? You will ask. It's a machine where you melt this material, this feedstock, and you push it in the mold. And the mold being cooled down, the part will solidify in the mold. You open the mold, you take out the part, and you can repeat the process. This is a process which is very well known on the industrial scale and which allows to make huge volumes. Once you have this part, it's what we call a green part. You will usually do debinding, either thermal debinding or chemical and thermal, to remove the binder. And then, so I do have a few, I don't exactly agree with the names here. The green body for us is just after injection. And then you have what we call a brown body after debinding. You put it in a furnace, you heat it up to make sintering, and you end with a metal part. So, and again, a small thing, what is sintering? Sintering is a densification of the part in the solid state. That means we don't melt the metal, we just heat it up enough that the part will densify. And you can see on the pictures that this densification means you're going to have a shrinkage, of course. A few common features about MIM-based technology in that case. The first thing is, in almost all of the case, the feedstock is going to be a mix of powder plus binders. Two to three step process, print, debind, and sinter. Sometimes debind and sinter is done in the same machine. Actually, you really have these three steps. You print, you remove the binder, and you sinter. And quite importantly, sintering means you'll have some shrinkage. And that has a lot of impact. It means you have some risk of deformation, cracks. You will also never reach a full density with a MIM part, except if you do some other post-process afterwards. But naturally, it's made for parts in the range of 90 to 95%. You need some support for sintering of metal. That's quite important. If you have completely unsupported places, they will probably deform because of gravity in the sintering furnace. And it's usually made for small and medium parts. So what I'm saying here is true for MIM. It's also true for all the MIM-based technologies. That's a common trait for all of these technologies, which really means this is great. I mean, that kind of technologies are really interesting. Of course, we play in that market, so we feel it's an amazing technology, but it really has some limitation, and these limitations are physical limitation linked to debinding and sintering. So you can't go around them by using another MIM technology. All of the MIM technologies will have that same common point. So let's start with probably the most well-known MIM-based technology, which is binder jetting. So how does it work? You'll notice that the schematic looks a lot like the one from selective laser melting. It was quite easy to draw for our marketing manager. The only difference here is that instead of melting with a laser, we're just going to solidify the part by jetting some binder on it, some solvent plus binder on the powder bed, which will make a solid part, basically some kind of glue, which will hold together the metal grains. And of course, then you need to sinter it to get a real metal part. So the pros of binder jetting, it's a very high-speed production. It's for small, again, for small and medium parts, it's probably the most productive technology. It's a low-cost process if you think per part. Again, you'll see it in the cons, but there's a high capital expenditure, but the price per part is quite efficient. You can go to relatively high thickness for a MIM-based technology because you don't have a lot of binder. You just have enough to stick the powder together, but that's not too much, and it allows you a relatively high thickness. It's possible to print internal features, channels, and so on. You just need to make sure you can evacuate the powder afterwards, so they can't be too small. And you don't need support for printing. You may need them for sintering, but you don't need support specifically for printing, because the powder bed itself will hold the part. On the cons, well, I should have started with that. It's a high capital expenditure. It's an expensive technology to acquire. It's not expensive to run, but it's expensive to acquire. It will get relatively rough surface, but I mean, it depends to what you're comparing. You can't print close porosities. And of course, there's this post-process, which is honestly a pain point. Debiting and sintering takes time. It makes for deformation and so on. So that's one of the defects. And last, it's still a technology where you use metal powders. You still have these questions of how do I implement it? Do I need people to be with full protective gear and so on? That's always difficult. Typical applications, just like with any other technologies, I'm a bit simplifying here, but I would say this is made for production. It's a technology for production. It's a technology for production of finished, quite complex parts or on-demand parts, but still, this is a technology which is used by people looking for volumes. Of course, we're very far away from what MIM, the real MIM technology will do, but you can print more complex parts, you can print smaller series. So it has really that range where it's made for production, but production of complex parts or production of medium-sized batch. Applications are, well, quite logically, most of applications are in high-volume industries where we will need production. Automotive is one of the industries where we see that happening. It's not the only one, of course. Again, I need to simplify because time is running. So it's, again, roughly 15% of the market. There's a few players here for us at the moment, but there's some big challenges on the market. But at the moment, the leader is probably X1. You also have companies like Digital Metal, HP, which is supposed to launch its technology soon. And of course, Desktop Metal is active on that market. And lastly, extrusion-based process, which is where Nanui is playing. So how does it work? Generally, there's a few exceptions to that rule, but the feedstock will be filaments. It could also be rods or granules or whatever, a mix of ceramic or metal in this case, and thermoplastic binder. You push it through an extrusion head, which will melt the binder, actually. You don't melt the powder, of course, but you melt the binder and you deposit it, and by cooling down, it solidifies. So it's really FDM, FFF of parts, except that the filament is a highly loaded filament with a lot lot of metal in it. There's two types of business model here. I just wanted to make a small focus on that. You have a few companies making what we call closed systems. The leaders in that range is Markforged and Desktop Metal. There's a few competitors, but that's the two leaders. This company, they aim at really providing a turnkey solution where everything is integrated. You have the software going with the machines, plural, because you need a printer and a furnace. Everything is integrated. It's supposed to be really easy to use. Honestly, it is usually quite an interesting point for this technology. Of course, that makes for more expensive equipment because you're paying for what you have, and you have a very complete solution. The leaders here are Markforged and Desktop Metal. There's a few challengers, but that's the main thing. And then you have an open system where you just provide the material and you say to the customer, you can deal with printer and furnace yourself, or you can supply the machines, but you don't force your customers to do it, which is what Nanui is doing. There's a small difference here between several filaments. On one side, filaments which are, let's say, mainly dedicated for outsourcing the post-process. And here the leader is BASF with Ultrafuse. And a few filaments, and we consider that Nanui with Dynamics is the leader on that part, where we aim at putting the whole process at the customer. What's the big difference between those two filaments? To make it simple, Ultrafuse on one side and Zetamix on the other side, it's the way you debine the material. Ultrafuse will use a catalytic debinding, which means you put the part into vapors of nitric acid. So you need a furnace that can supply that nitric acid for debinding, and then you need another furnace for sintering. And in the case of Zetamix, we're doing a thermal debinding, which means we're using the same furnace for debinding and sintering. That's the main difference. Apart from that, the technology is really the same. But how does it end up? It ends up in one side, Ultrafuse, BASF will mainly recommend you to outsource the post-process, because putting it in-house is quite expensive. We've put a figure here. It's not very precise, maybe a bit less, a bit more, depending on the equipment you acquire, but that's the rough range. And our philosophy at Nanui is the other way around, which is to say, we want to put the process at the customer. We feel it's interesting for the customer to really be independent and to close the loop and to be faster. And so we adapted our filaments so that they could be used with simple furnaces. And we have a package that is compatible with all of our filaments except 316L, which start at 10,000 euros. And we feel it's a big pro. I'm not saying one of the business model is good and the other one is bad. It really depends on what you want to do. Some people just are perfectly happy with outsourcing post-process. It's more simple. You don't need to install any machine. It's convenient, and for them, honestly, they should go for Ultrafuse. And some people will want to have the technology in-house because they have sufficiently volumes, because they want to learn about it, and that's the right way to go for it. So the pros and cons. On the pros, it's a low-cost process. Of course, there's a difference in price band depending on which machine you acquire, but still, it's relatively low cost in terms of investments. It's easy to use. That's really the two things we put forward with our technology. We say it's easy to use, it's affordable. It allows to print internal channels. It allows to print close porosity, which is really a big thing, actually. It may not seem important, but that's really a big thing with FDM. And it allows to, it avoids any powder handling, which is a big advantage. On the cons, it has a, medium precision. It's not the most precise technology. You will really see the lines on the surface, and you still have that post-process, which is still a problem, honestly. You still have risk of deformation, limitation in size. All of this is true for that technology also. The typical application, well, here, of course, we put some parts from Nanoe, but you will probably see the same at our competitors. This is, I'm not saying there's not other application, but this is a technology made for tooling and internal uses. That's where it's really the best. The kind of parts we can see here, you have some fixtures and jigs. You have here, it's an extrusion on the right, an extrusion head for extruding our filaments. Any kind of internal tooling where you may need on-demand parts, you need them quick and fast, you need them, you don't necessarily need the highest level of precision, but you need it to be reliable, and especially you need a high-strength material, so you would go for metals and also for ceramics. Again, it's a small, around 15% of the market. And a few players here, I put it on top the open system, and on the bottom, the more integrated systems. So I talked about BASF and Nanoe. There's Virtual Foundry in the US. There's a few other players, I can't name them all. All have different characteristics. But yeah, it's kind of the same model. And of course, for the more integrated systems, Markforged and Desktop Metal are clearly leading, and by far. You have a few companies trying to challenge that. In France, you have Poland, which has a different technology. It's extrusion of granulates. You have a company called Rapidia, I think it's in Canada, which is on a extrusion of water-based paste. So it's a bit different, but still in the same kind of principles, which are trying to challenge a bit this domination of Markforged and Desktop Metal. You have other technologies. I can't name them all, and I'm probably forgetting some people here. SLA Metal is starting to get a bit of traction. We know two companies doing that, which is Admatec and Incus. Interesting for very small precision details. Inkjet is a bit in the same thing. You could do very precise parts. We've heard of people making metal with selective laser sintering of plastics by putting metal in plastic binders. There's really a lot of possible technologies, but let's say we've named the main ones. The final takeaway is that we really believe at Nanoe that there's no competition between those different technologies. They're all complementary. So the right question is, what is my application? What do I want to do with metal additive manufacturing? Once you know that, you can choose the technology. You should really do it that way and not the other way around. If you start by saying, yeah, I want that technology, and you ask yourself afterwards, what can I do with it? You're probably taking the problem in the wrong side. So you should really, really start with the application. If you have the application, you'll find the right process for it. Of course, raw materials are key here. That's something we believe strongly at Nanoe. We are a raw material producer, so we believe raw materials are the key. And apart from FDM, which is really our main focus at the moment in additive manufacturing, we are also sometimes developing adapted raw materials for other processes, and that's also something we are clearly willing to do. That's it for today. Thank you for your attention. I'm going to try to answer to your questions. Hopefully they won't be too difficult. First question from Frank. Can you switch in the furnace from argon to hydrogen, or do you have to decide when you invest in the equipment? Well, I'm going to talk for Nanoe. It might be different from others. Usually you don't use the same equipment for a furnace that will use hydrogen or a furnace that uses argon. Because if you use hydrogen, you need a much higher level of security on the furnace, because of course, hydrogen can be explosive. To put it simply, a furnace that can use hydrogen can use argon, but a furnace that can use argon can not necessarily use hydrogen. There's something in between also. You can also use mixes of gas, and a mix of argon and hydrogen with a low content of hydrogen will have less explosivity, and at some point it's non-explosive, and you can use it in a standard argon atmosphere. I hope this is clear. I'm not sure. So what makes direct energy deposition with powder different from powder bed fusion method? That's a good point. The big difference is, well, you don't have a powder bed. You're depositing exactly where you want the material, but you don't have the powder bed, which will have a big impact on the kind of geometries you can make. It's still two different technologies. Yeah, the big difference is you don't have that powder bed as the base for your building. So a question about cold spray not being so used at the moment, mainly as coating solution. That's true. Cold spray is also used a lot for coating, of course. Is there some potential for this technology in the field of AM? Well, I must say I'm not a big expert on cold spray, and so I don't know if I can answer very well to that. There's a few strong features with cold spray, and one of them being it's really very high build rates, and some companies are focusing on that and saying basically it's a technology to make preforms, very big ones, and then we know we're going to post machine, but it's acceptable. It's just a way to make a preform instead of machining really from bulk material. Will save some material. I think it's a clever approach. It's also something you could do with direct energy deposition. Honestly, hard for me to answer on the future of the technology. I'm pretty sure it has a future, probably a bit niche, yes. Do we need glass transition temperature for printing? I guess this question is about FDM printing. Well, in FDM printing, basically what we even melt is we melt the binder. So usually we go to temperatures where we have more than glass transition. We really have a melted binder, and the powder is still in it. So that's usually goes really to the melting of the binder. What makes the difference between ultrafuse and Zetamix? It's really the binder system. The key point in this technology is what you put inside your binders. This is where we've been working a lot, and of course BASF also. The ultrafuse comes from a feedstock which is used for metal injection molding, but it's a great material. In our case, we really worked a lot in developing binders so that we have something more simple. We started with chemical debinding, which was already for us a step in the right direction, and now we're trying to, well, we are more than trying. We've switched the metals to thermal debinding, and what makes the difference is the binder formulation. What about the cost of Zetamix filament compared to real ultrafuse? So you're quite right in the price point. We're more expensive than ultrafuse in terms of price per kg. We feel it's not that important. Of course, I'm not very objective here, but we feel that's not that important if you actually calculate the cost, the total cost of the part. What will make the cost of the part is in this technology is not the material. It's going to be the post-process. It's going to be the investment if you decide to acquire the equipment. I must say that BASF has a very cost-effective technology if you're willing to outsource the post-process. If you're willing to do that, the price point is very good. You must recognize that. In our case, we're really trying to focus on if you want to have the technology in-house, the cost per part needs to be reasonable, but the cost per part will come from investments and consumables, not from the raw material itself. And if you want to have the technology in-house, I can say quite confidently that we have the most cost-effective solution. Carbon and graphite powder. So we haven't worked with carbon and graphite. I must say I can't answer that question. I'm sure there's some application, but it's a material I'm not very familiar with. I'm just gonna leave it there. And the market shares, that's really, it was just to give raw figures. We took it from a study from Aniwa, I think. I must say, I can't answer the question precisely. Is it the revenue for the machine, for the powders? Probably for the machines. And I don't have precise value. It was just to give an idea that for the moment, the #1 technology for metal is clearly powder bed fusion. The other ones are equivalent. We see a strong dynamic for binder jetting at the moment, really, and for FDM, but the other ones are quite equivalent, and cold spray is a lot more niche for the moment. But I can't give you more than that. So just to give rough ideas. Shrinkage in XYZ and volumetric in percentage. So that's a good point, a good question. If we start by volumetric, which is really a good question, it's quite one of the difference between several filaments. When you look at a filament, everybody's going to say, yeah, we have a huge amount of metal in the filament, which is quite easy to say because if you talk in mass percentage, since the metal is very heavy, well, you have a lot of metal in the filament. And what you should look at is how many metal powder do you have in the filament by volume. And at Nanoe, we always focus on having more than 50 volume percent, 50 to 52, 55% in volume of powder in the filament, which allows to make a good dense part with a reasonable amount of shrinkage afterwards. It's not the case of all filaments, and you should really read the small lines. And to give you an idea, 50 volume percent will mean more than 90, I think it's 92 mass percent, I'm not completely sure, of steel in the filament, if you talk in mass. So that means that the shrinkage, if you have 52% of powder, and at the end you have a 90, 95% density, you're going to have a volumetric shrinkage of 40%. In XYZ, that means something like 20%, roughly. Sometimes it's a bit more, a bit less, depending on the metals and ceramics, but in general, it's 20, and it's not exactly the same in X, Y, and in Z. So how to measure the porosity of different materials? Well, we're talking here about the sintered parts. What we usually do, if you have a dense enough material, let's say more than 90% density, you can measure it quite simply by Archimedes measurements. That works really well, supposing you don't have close porosities, because if you have close porosity, you're going to measure a false density. So we do that on benchmark parts, on simple, fully infilled parts, and then we say, okay, all of our parts are in the same range of density. How long does the sintering takes for average sized parts? So I'm going to say debinding and sintering. So that depends on the kind of technology. In our case, the fact that we use a thermal debinding makes the process quite long. It's one of the trade-offs. We find it more simple to use, but it makes for a longer process. So the total time is going to range usually in the roughly around 3 days, I believe, 2 to 3 days. I'm not completely sure, but something like that. This is quite long, and that's something to have in mind. How do we avoid deformation cracks for MIM technologies? That's a complex question. There's a lot of answers to that. The first one is you need to be very careful about the process itself. You need to learn how to, well, you need a furnace that's going to have homogeneous temperature, of course. You need to be careful about controlling everything in the printing and sintering process so that you don't put any stress on it. And there's also a big side of it, which is about designing for this technology. We talk a lot about design for additive manufacturing. We should go one step further. It's designed for one AM technology. And if you do MIM-like technology, there's some work on designing specifically for that technology. We're going to do another webinar on that at some point. We already did one. So that's an interesting question. What is the missing part in metal printing? What are the biggest challenge in metal printing now worldwide? I don't know if I have one answer to that. I think metal additive manufacturing, metal 3D printing is developing very fast at the moment. I would say it's working well. We at NanoE, we have one focus, and we think it's important in developing metal and ceramic additive manufacturing. We feel it's crucial to have affordable desktop solutions for these materials. If we have that, we're going to have a lot more people using the technology, learning about metal printing, seeing what you can do with the technology, and it's going to help develop the whole market. So that's our focus, making the technology simple and affordable to make it a lot more mainstream. That's what we want to do. So massive part production, how do you see benefits in comparison to casting technology? That's an excellent question. Casting is not going to be replaced anytime soon. And by the way, you can combine casting and additive manufacturing by printing the mold. A lot of people do that, printing ceramic cores, printing molds, printing sand molds. There's a lot of work on that also, and I didn't mention it. I could have mentioned it. It's, let's say, almost an indirect additive manufacturing technology. So there's no way this is going to be replaced by DED, but you do have a few cases where it's going to be interesting to print it instead of casting it. I'm not sufficiently expert to tell you. I can tell you in the example I showed, which was the part from Naval Group, the propeller. One of the interests is they made it completely hollowed out. You could do that by casting, of course, with a core, but that was probably more simple to do with I think it was in the one, but I'm not sure, the direct energy deposition. What about vacuum furnace? If you use vacuum furnace on metal, I must say, I cannot answer to that question because we haven't made enough tests to answer it. It is used in the MIM industry, so it should work to use vacuum furnaces. I can't tell you exactly what kind of vacuum you should need. Advantages of EBM to SLM. Again, I'm not a big expert here, so what I'm going to say is a rough picture. The first advantage, I believe, of EBM is it has relatively higher build rates. And another advantage is in terms of construction of the printer, it's much more simple because directing an electron beam is mechanically extremely simple. Basically, you take a very old television set, you have something that directs an electron beam at the bottom of it. So this is quite simple to implement, at least for directing the electron beam. I'm not talking about the rest. So that's some of the advantages. I think it does make a bit more rougher surfaces. Well, that's it. I can't say much more. alloy deposition. So I don't know which technology you're talking about. I suppose that's for FDM. Theoretically, you can print a lot of different alloys with FDM, any alloys that can be sintered. To give you an example of something which is difficult, not going to say impossible because we hear about it at the moment, aluminum alloys have always proved to be very difficult to sinter, and so it's difficult with this technology. But any alloy that you can sinter, you could print. There's a bit of work to develop the filament, but it's possible. I think I already answered to that one on processing time and all that. Are you developing more filament at H13 and 316L? Yes, we will, but nothing in the short term, but we will certainly. Can you use ballast powder to stabilize the part during sintering and avoiding warping? Yes, that's a possibility. It's difficult to do precisely well, because it also have defects, but it can help. It's a solution to support a part during sintering. Any health and security environment precaution when using your debiner and sinter furnace? Yes, of course, quite a few ones. The first one is debining when you need to do chemical debining. So for ceramics, the solvent is acetone. So acetone is very volatile. So that means you need to be under a proper fume hood to avoid any accumulation of gas. And it's a bit the same thing for sintering. You're gonna have a flow of argon, you're going to have a lot of heat, and you also have some burnout residue. So we are pyrolysing the binder, so you need to make sure that you're not going to breathe any of that. So usually we do more than recommend. We insist on the fact that this needs to be under a fume hood with extraction of the fumes. That's really critical. Apart from that, the fact that we're not manipulating powder makes it a little bit more simple. Is this technique well qualified to process high ratio of ceramic plastic compound? Yes. Yes, it is. We also supply ceramic filaments, so absolutely. It's a good technology for that. And the ratio is more than 50 volume %, absolutely. So what is the max volume and max temperature of Zeta sinter? Can we do vacuum sintering in vacuum or in that gas atmosphere? Temperature goes up to 15 degrees Celsius, even 1600, but we try to avoid going too much at that temperature. We usually use it under air for ceramic and under inert gas for metals. We don't sinter under vacuum. Because that's a bit more complex to do. The most challenging is the standard for evaluating the properties. That's definitely a question. I agree with you. Another topic for next webinar. In a 3-day sintering process, is the grain size growing a lot. So the grain size is growing, but you need to understand that in the 3 days, most of it is actually for the debining and not for the sintering. It's for the thermal debining in a range where you don't grow the grains. You do have a bit of grain growth at the end, but the sintering phase is a lot shorter. So printing multi-materials, so ceramic and metals in one part, that would be really very interesting. It's a big challenge. There's a lot of people working on it, some people working without technology on it, some laboratory, but it is very difficult. So I would say not in the near future. In the long future, yes, and there's some huge application for multi-material printing ceramic and metal, but it is difficult, really. How much is the precision and resolution of this technique? I guess, again, we're talking about FDM. I didn't precise that, I should have, but in most of the MIM-based technology, precision is going to be limited more by the sintering and the shrinkage than by the actual printing. Of course, binder jet is a little bit more precise than FDM, but not that much, because anyway, we're going to have to sinter. And sinter is going to play havoc with precision, and it's really the difficulty. What we usually say is, for a part that you know well, and a material that you know well, good precision would be plus minus 0.1 millimeter, with parts up to, let's say, 5, maybe 10 centimeters. This is really the best you can reach, plus minus 0.1. Other geometry you have already done at least once. That means repeatability. If you print a completely new geometry, you may have deformation you have not anticipated, you may have other things coming in. So it's not the most precise technique. And anyway, sinter-based printing has a limitation on precision. Almost 1 to 2%. Well, 0.1 millimeter compared to 100. No, I would say a bit better than that. A bit better than that, but again, it depends if it's the first time you print that part or if you've printed it several times. Yeah, that's it. I think that's all. Oh no, there's some questions in the chat, so I'm going to switch to the chat. Yeah, well, I'm sorry it's not Suzanne doing this this presentation, but I'm sure that for the next one it might be Suzanne. I would like to have some feminine faces for some webinars. We felt that this webinar was a bit well, that's really very technical, but certainly you'll see Suzanne in the next one. Okay, so there's been some. So what is the max volume and max temperature for the Zeta sinter? I think I answered it already. Max volume is, well, it's a tube furnace. So that means it needs to fit in the tube, which is a 10 centimeter diameter. That's really a big limitation, actually. And the max temperature is 1600 degrees Celsius in peak. We would rather stay at 1550 maximum if you really hold it. Of course, we'll send the slides. Ideally, if you could put your contact info in there was a link in the LinkedIn event. There was a link to a Google Sheet, to a Google form. If you can fill in your contact info, then we can send you the slides and even probably a replay of the webinar if you want to follow up to some other people. Can you talk about new material plans? Well, the metal are already based on the thermal debinding system. We're trying to adapt that for ceramic, and this should be released this year. That means before we release any new material, the first thing we're going to do is update our current materials so that they become available for pure thermal debinding. We have found out that the solvent is an issue for a lot of our customers, so we try to remove it. Of course, you'll have the slides again. Thanks you for the nice comments. I think I've answered to most of your questions. Of course, if you have any other question, you're more than welcome to ask them, and you should keep following us on LinkedIn, of course, so that you will hear about the next webinars. We try to do it every 1 to 2 months, so I'm sure we'll have some new stuff soon. And of course, you can also suggest us if you want us to talk about one topic specifically. You're more than welcome to ask, and we'll try to answer these. The microstructure of materials. Okay, well, we can do something about this. If you follow up on LinkedIn, we're going to publish some work soon on microstructure and mechanicals for ceramic materials. Metal will come a bit later on, but yeah, you should follow up. That's going to come. Well, thanks again for attending. Except if you have any other question, we're going to close for today. And I hope to see you at our next webinars.